Hello, folks. Thank you again for joining us here at the plenary today on day 3. This is an exciting day because we get to actually see some extraordinary continuation of the science program. But we actually start off with an even greater treat, which is an overview of the Goldschmidt conference for next year, for 2015. And it is my very great pleasure to introduce Dr. Eric Olkers of the European Association of Geochemistry, who is going to provide us with this preview of the Prague conference.
Hi. Actually, I'm going to do two things. Notice I'm a little bit loud. Now, like me, and I imagine like many of you in the audience, have like two thoughts at about this time in the meeting, okay? The first one is, now actually, do you have a slide? Is my slide on? Good. The first one, and there's one of two, is like, I just produced some really, really, really hot science, some really great ideas, and if I get this right, do I push a button here to make this thing go? How does this work? Green button. Thank you. So, you know, you're thinking, oh, and red is probably this thing. Well, anyway, the point is, you're thinking, hey, it's really, really good geochemistry, but, you know, science and nature, they just, they just don't publish that research. And if you're like me, they usually send those papers back as soon as they get them saying, we're not interested, okay? But then equally, you don't really want to write that 20-page paper that you need or seem to need to go into these other journals. And so, in an effort to fill this niche, the geochemical societies are in the process and have started a new publication initiative to sort of pull in between the two. And it started, and many of you have seen it, with geochemical perspectives, and we're getting our first impact factor within a couple of weeks, and it seems to slide right around here in the hierarchy of things. And many people have now saying, okay, what do we need now? And many people have asked to submit into this and put this, and we've now starting, and I announced to everybody that we're starting now a new letters section of geochemical perspectives that's starting this year, and it's going to take short, snappy, topical papers for those things that those great ideas that you're just not ready to write that full paper in, and sort of slides in there in our family of journals. And just some of the details here: short, high snappy papers, articles available on the web as soon as they're accepted, free to publish, free open access, available on Geoscience World. Published versions of this, when they're ready, go out to everybody for free. This is a society initiative. This is we publishing for us, okay? We're not doing it for a public company or anything like this. And we're going to sort of have an official launch party at the 23 Goldschmidt. And so it's available on the web. And the second thing, of course, is you're all waiting for, and I'll just be completely brief because Prague sells itself, and I know you're still thinking about bits and pieces of Sacramento, but just keep in mind August 16 to 21st, 2015, we're going to Prague. And well, you know, we all know Prague. You know, and one thing I have to say about Prague, as you might have already forgotten, you know, there are some cities in the world that people will visit even if there's not a conference there, okay? And Prague's one of them. It'll be a good time. And the only other thing I could really promise now, because I know you guys are already thinking of the great science you're going to present there. And you know, you're going to be the real stars, but the most important thing that at least I can say as head and conference, or head, I guess, what is a coordinators meeting, is that I promise you on my scientific reputation, my reputation as a gentleman and as a scholar, free beer, and as much beer as you care to like during the poster sessions. None of this ticket nonsense, okay? So, put it on your calendars. Prague will be a good time. And now, thank you for your attention, and we have our main feature presentation. Chris?
Well, as current president of the Geochemical Society, when they ask you to think about whether you want to get involved with these societies, one of the things I always do is say, I take a look at the people that you'll be working with. And across both the Geochemical Society and the European Association of Geochemistry, they're an outstanding team of people. But I have to admit, a very, very big part of being willing to get involved in some of the work of the societies is the opportunity to work with someone that you actually already work with. And it's an enormous pleasure for me, in particular, to introduce Christopher Ballentine for his plenary lecture, as we have been working together in various capacities for longer than I think either of us cares to admit at this point. So I'm sure, as many of you know, Chris got his PhD from Cambridge and has spent much of his scientific career really driving innovation in the use of noble gases and looking at these in a variety of contexts, from subsurface water to hydrocarbons to mantle-derived processes, with a particular focus on an innovative application in continental settings. His interests also expand to look at how the Earth has gained its gaseous inventory and processes controlling reservoir interaction and evolution over time. His career has taken him to Switzerland, I believe originally, to Michigan, ETH Zurich, Manchester, and of course most recently as the chair of geochemistry at Oxford. Most of you may know him as well, of course, for the really leadership he has brought to the EAG and to the development of the European Goldschmidt conferences, working heavily in those since 2007, chairing Davos in 2009, as a Goldschmidt officer for Prague in 2011 when we were first there, and most recently as, of course, co-chair of the hugely successful Goldschmidt last summer in Florence in 2013. Without further ado, then, it's my great pleasure to introduce the current president of the European Association of Geochemistry to provide you with a lecture about what he does on his day job.
Thank you, Barbara, for those very kind words. It's certainly a pleasure to be here, and as president of the EAG, I would like to say before I start my lecture, a huge thanks to the GS, Barbara, the local organizing committee for such a wonderful conference and such exciting science that we're seeing at this conference today. Okay, so I'm talking about volatiles in the Earth's mantle, and no work is complete, no work achieves the level you want it to achieve without a huge amount of input from a variety of colleagues. And I certainly want to acknowledge my colleagues who have contributed hugely to the work that I will be presenting today. I have to slightly apologize because while it's good to start a lecture with a bang, this is an artist's impression which is physically wrong in so many different ways. But at the same time, it really does emphasize the high energy processes that our solar system started with, the processes that formed and created the Earth, the energy available to melt the Earth, to generate magma oceans, and to bring the volatiles to our planet. My next slide, to me, is one of the most scary pictures I have. This is a fantastic photograph from NASA showing moonrise, and really just emphasizes the fragile nature of the environment that we are in. We stand outside looking at the bright blue sun, and we think, well, this is fantastic. This is something that has existed for 4.5 billion years, but look at how fragile that is, how thin that atmosphere is. This is a thin veneer around our planet. Our planet is gas poor. We've lost the majority of the gas from our planet, and what is left is what sustains us, sustains our society, and has sustained life over Earth's history. So bringing these two components together, we can start to think about the processes that formed the Earth. We can think about whether or not there was solar nebula gases present that were captured by some of these protoplanets. We can think about volatile sources being brought to the planet through meteorites, gas-rich rocks, icy bodies. together forming proto-atmospheres in these early bodies. The energetics, as I've already mentioned, will almost certainly have generated a melt on the planetary surfaces, allowing equilibration between whatever constituents form that early atmosphere and the deeper planet. The deeper planet, with the magma ocean, will take those volatiles down into the planet. Solid phases will form. Convection within the solid phase can again take early atmosphere components down into the deep Earth. There may be even remnants of early accreting material that hasn't degassed. We don't really know. But what we do have today is an Earth where we can sample the deep Earth through mid-ocean ridges, through ocean island basalts, through other avenues that provide us with an insight into the volatiles inside our planet. And we are looking for the volatile fingerprints, the volatile traces that may give us an indication of these early processes. So what sort of timescales are we talking about? When did the Earth really stop its accretion of gases? I should say really, when did it start its accretion of gases? We've got a chronometer. There are two isotopes of iodine. 127 is the stable one. 129 iodine has got a very short half-life, 15.7 million years. Iodine 129 decays to xenon 129. And we've got a fairly good idea of the bulk silicate earth content of iodine 127. From meteorite studies, the ratio of iodine 127 to iodine 129 at the start of the solar system. We therefore know, to a reasonable degree of accuracy, the amount of 129 xenon, a gas, that should be that our planet should have. It's just not there. This is a direct measure of the volatile loss our planet has undergone. We can see 0.8% of what we predict from bulk silicate Earth 129 iodine. We've suffered a minimum loss of 99% of the gases that were available to form our planet during the accretionary process. A huge, huge loss. That's only placing a lower limit on the amount of gas we've lost. More importantly, it's giving us a chronometer. It's telling us when this happened. George Wetherill first identified this as a planetary closure chronometer back in 1975. Pepin and Finney in 76 also recognized that another series of xenon isotopes were generated by plutonium, also a short-lived isotope, also only available in the early solar system. Slightly different half-life, 80 million years. And let me just go back one. Rather than relying on the xenon to iodine ratio, we're able to derive the closure age for the planetary atmosphere based on a series of parent element abundance ratios, the uranium-iodine ratio, the plutonium-uranium ratio, and a series of isotopic ratios. It's a more robust chronometer, and you're using two different decay schemes to provide a higher degree of confidence that the closure age that we're measuring for when the planet stopped losing gas. This is a single-step model. It assumes that the planet did not retain gas up to 100 million years, and then after 100 million years, it was closed to any significant atmosphere loss. It's very interesting. Pepin and Porcelli in 2006 noted very similarity in the xenon isotope ratios in the mantle to those in the atmosphere, and argued that the closure age for volatile loss in the Earth's mantle was the same as the closure age for the Earth's atmosphere. In other words, the entire planet was open to volatile loss until about 100 million years after accretion started. At that point, our planet trapped its atmosphere and has evolved subsequently. So we've got a time frame in which we can interpret or develop our understanding of the volatile acquisition. This is a numerical simulation of planetary growth by Canup, showing how fast Earth might be expected to grow. So we're looking at Earth growing, in fact, in about 100 million years, looking at about 90% accretion in about 100 million years. Within the first 10 million years, we're looking at protoplanets on the order of 30 to 40% the size of Earth today, so Mars-sized bodies and a little bit bigger. These are significant sized bodies which are forming, most likely, in the presence of solar nebula gases. So these are planets that can capture an atmosphere of solar nebula composition, but the planet is still evolving, highly energetic, with a lot of processes that are capable of removing the atmosphere. So in less than 10 million years, Mars-sized embryos and nebular gas is present. That gas almost certainly can equilibrate and leave its imprint in the planet, but through the rest of the accretionary process, the degree to which those volatiles and that signature of a solar nebula gas survives is something that we can test with observations. There are other sources of gases. We know that carbonaceous chondrites are incredibly gas-rich and can certainly supply the volatile inventory of the Earth. And icy bodies and other sources of volatiles are also possibilities of providing a volatile source during the planetary growth or later. The tool of choice that I've used to investigate this are the noble gases. So noble gases, we've got a good number of isotopes to play with. We've got 23 stable isotopes from neon through to xenon. Importantly, they're chemically inert, so they survive, they preserve the record and the fingerprint of those sources throughout the different chemistries and processes. They do respond to physical processes such as mass fractionation, but they're far more simple to understand than the range and array of chemical processes that some other elements you need to take into consideration. I'm not going to talk through all 23 isotopes, don't worry. We've got 3 classes of noble gases that are little affected by radiogenic processes, often called primitive isotopes or shielded isotopes. A number of isotopes are the targets for preserving those planetary volatile sources because they're not contributed to by other effects. We have isotopes which are dominated by long-lived radioactivity, helium-4 produced by uranium and thorium decay, argon-40 by potassium decay, and a range of nucleogenic processes which, because of the noble gas low abundance, become significant components in the isotope system. And I've already talked about xenon, which is one of the noble gases produced by radioactivity that's now extinct. So I think everybody, I hope, has come across one of the key uses of noble gases, helium-4 to helium-3 ratios. Certainly it's a classic tracer for understanding the different volatile domains which are in the deep Earth. This is showing the helium-4 to helium-3 ratio in mid-ocean ridge basalts, a fairly uniform ratio, suggesting that the mid-ocean ridges sampled by 65,000 kilometers of mid-ocean ridge, sampling that bulk mantle, is fairly well mixed with respect to the radiogenic and the primordial noble gases. Effectively, the solid to fluid ratio, solid to gas ratio, is fairly well mixed and constant through that portion of the mantle. Quite different to ocean island basalts. This is showing some classic places, Iceland, Hawaii, and we can see that these systems quite often have a helium-3 enrichment, which has been used to suggest this is a volatile rich domain, and a volatile rich domain because of the nature of helium, which has been preserved over the lifetime of the planet. So we have at least 2 volatile systems and reservoirs in the mantle which have survived over planetary time. Certainly a classic model for relating these two to each other has been that the ocean island basalt source, volatile rich, has provided a flux and a source and a reservoir to provide the helium-3 seen in the mid-ocean ridges today. So this is a classic tracer which has been used to provide an understanding of how Earth's volatile reservoirs have changed over history and the different domains within the mantle system. So this allows us to address, the noble gases allow us to address some really fundamental questions. By asking what the origin of the noble gases in the mantle are, what are the primary sources of those noble gases, we immediately start to gain a unique insight into planetary accretion processes. Where in the mantle are the primordial noble gases? How are they preserved? This gives us information about mantle structure. And how has the noble gas composition in the mantle evolved over time? How does this relate to the ocean atmosphere system? This gives us an indication, not just an indication, but with the right measurements and with the right tools, it allows us to quantify the degree of interaction between these fundamentally different domains within the deep Earth system, and certainly how they relate to the planetary surface. I want to show you how we use neon isotopes to distinguish between some of the planetary volatile sources. We've got 2 principal sources of volatiles in the Earth. I've mentioned that a little bit in my introduction. Whether or not the Earth has captured solar nebular gases, whether it preserves a record or evidence of solar nebular gas within its deep interior. Or another possibility is that the volatile source has been delivered in accreting material. So volatiles which are trapped within, for example, carbonaceous chondrites and brought to Earth through trapped in accreting material. Neon is particularly interesting because meteorites which have been exposed to solar wind have got a unique and distinct isotope composition compared to solar nebular gases. So if we want to identify whether or not the volatiles in the deep Earth within the mantle preserve a solar nebula composition, or whether they might be solar wind irradiated samples, neon potentially allows us to test these 2 different models of planetary volatile acquisition. Solar, it's got a distinct isotope ratio in 2022. Neon B is the solar wind implantation, quite distinct from modern atmosphere. And we can look at the database of meteorites. We can look at meteorites with high neon concentration. Very interestingly, these are gas-rich meteorites. The gas-rich ones are regolith samples, heavily irradiated. Note the log scale, and also note that the highest concentration samples contain this signature of neon B, this signature of solar wind irradiation, and mass balance. From this database, you only need 1% of this material to account for the neon in the deep Earth. And Frank Podosek in 2000 also did a very simple mass balance calculation and showed that the neon in the Earth could be generated by solar wind exposure of 3-kilometer radius spheres over a period of 1 million years. So because the planet is so heavily degassed, it doesn't require very much of solar wind irradiated material to actually provide its source. The question now is that the source of neon in our planet? We can look at some of the some early high-quality data from Mario Trilov back in 2000, looking at ocean island basalts, looking at Hawaii, looking at Iceland. This is the 2022 ratio. And Hawaii, Iceland, the data all peter out at about 12.5, suggesting that the deep Earth, the mantle source of the ocean island basalts, was supplied by solar wind irradiated material. It's an inconclusive test because how do we know there isn't something a little bit higher? And in fact, a few years later, Raika Yakochi in Bernard Marty's laboratory, Sujoy Mukherjee, very soon found evidence for significantly higher neon isotope signatures within the Kola Peninsula plume environment and also samples from Iceland. Certainly providing a hint, if not proof, that there is some sense that the planet, the deep planet, may have captured a signature of solar nebular gases from the very first stages of planetary accretion. But what about mid-ocean ridge basalts? What about the dominant portion of Earth's mantle? This is some really fantastic data produced by Manuel Moreira a little while ago now on 2πd43 popping rock. This is a very volatile, rich rock called the popping rock because erupted at pressure under the water. High pressure vesicles brought to the surface, and the vesicles just erupt and pop and break. But because it's so gas rich, it's a fantastic sample resource to gain an insight into the volatile composition of the mantle supplying mid-ocean ridges, and it's often been used as the reference point for our understanding of mantle volatiles in the mid-ocean ridge mantle source. Looking at the neon isotopes, the 20-22 ratio, again, air is down here. The samples are invariably contaminated a little bit by air, just by erupting into an environment that contains air. But the highest ratio measured in the mid-ocean ridge basalts is, in fact, about 12.5. So if we want to ask the question, does the convecting mantle supplying mid-ocean ridges preserve a solar nebular ratio? It's not obvious from this sample. It certainly looks as if it contains the signature of solar wind irradiated material. But remember the lesson from Hawaii and Iceland. Just because it peters out around 12.5, around the solar wind irradiated signature, does not mean that is the top upper limit for that sample. So we've got a new way of looking at the mantle supplying mid-ocean ridges, the mantle, the shallow mantle. And it's looking at a different sample resource. Rather than looking at the mid-ocean ridge basalt samples, let's look at other systems which sample the shallow mantle and bring shallow mantle volatiles to the Earth's surface. We find them in natural gas fields. Wherever you look in extensional basin systems, you will find three components in a natural gas. You will find noble gases generated by radioactivity within the crust. You will find noble gases brought into the deep fluid system, dissolved in groundwater. And invariably, there'll be a small trace of magmatic fluids in the background of your samples. It's a diagram showing some of those components and how they may mix and eventually be found in the gas well, the gas field that you're sampling. Now, we've looked at carbon dioxide-rich fields in great detail because there's a huge amount of interest in the way carbon dioxide behaves in the subsurface. For carbon dioxide burial, for removal of anthropogenic carbon dioxide, we must know how carbon dioxide, what the sources and what the sinks of carbon dioxide in geological structures actually is. So this is one of the fields we've studied extensively, and I just want to show you the helium isotope contours, just showing you how well behaved this sort of system is. We've got a 3-4 ratio, about 1 Ra moving up to 4 Ra, that's times the atmospheric ratio. This is higher and higher and higher mantle signature in this particular system. And we understand the system very well because we've taken it to pieces and trying to understand the sources and sinks of carbon. But now we can look at just the magmatic component. within this gas field. It's a unique sample resource. It's magmatic gas, which instead of degassing to the atmosphere has been trapped in a geological structure. The carbon dioxide is clearly not from any other source. It's in place deep and recently, which means it's contacted very little of the groundwater system. It's very low in that atmospheric contamination, which is ubiquitous in all samples we look at. We've got unlimited sample amounts. Think of this gas field as a giant fluid inclusion 50 kilometers across. We can sample bits of that gas field and look at the systematic behavior of the noble gases and understand exactly what that mantle end member looks like. This is located in New Mexico. We've got surface extrusions, intrusions. There's a nice photograph of a capulin cinder cone. All of our samples are taken from boreholes, drilled into the ground and commercially produced. You may not be aware that the oil industry extracts a large amount of carbon dioxide from systems like this, which they can then pipe to, in this case, the Texas Permian Basin, inject it into the ground, and it enhances secondary oil recovery. But the neon isotopes in this magmatic gas-rich system have provided a unique insight into that mantle source. Unlike mid-ocean ridge basalts, which are always a mixture of air and somewhere up here where the mantle end member lies, the crustal gases have provided us with a natural experiment. The groundwater does not have an air isotopic composition. The groundwater has been sitting there for a very long time, and the groundwater has evolved with a radiogenic crustal, radiogenic isotope spike, if you like. The groundwater sits with a very distinct isotopic composition, and when the magmatic gas is emplaced through the groundwater, contacts the groundwater, we have simple mixing between our spiked atmospheric end member and the magmatic component, allowing us to look at the simple intersection of the mixing line found in the continental setting with the mixing line found in mid-ocean ridges to identify that we have in the shallow mantle a neon B signature. Certainly a ratio of 12.5, which we can interpret as being indicative of solar wind irradiated accretionary material being the principal source of the noble gases and associated volatiles in the convecting mantle system. We've got 23 noble gas isotopes. It would be very worrying if this only worked for neon. It doesn't. We can look at the xenon isotope system, which behaves in a very similar way. I'm looking at some of the radiogenic xenon 136, produced by uranium decay, one of the extinct nuclides 129, but all of the mid-ocean ridges have exactly the same systematic behavior as the neon, where we have simple mixing between an air component and the mantle lying up here somewhere. Our crustal fluid system, our groundwater, has been evolved by accumulating radiogenic 136 xenon. When that magmatic gas is emplaced, we form a unique two-component mixing line which intersects the mid-ocean ridge basalt air mixing line to give us our mantle value, which correlates exactly with the xenon value we would predict when neon 2022 equals 12.5. So we have a variety of isotope systems which are completely compatible with the derived value for neon, which we then can interpret to be solar wind irradiated material. But what about the heavy noble gas? I've placed very much emphasis on solar wind irradiation. What about trapped components? What about nebula gases that may also be within that mantle system? We can look at the argon isotopic composition. We've now got the ability to measure noble gases with a precision using new multi-collector technology with a precision which is unprecedented. We've brought up the precision in the ability to measure these sorts of samples by between a factor of 10 to a factor of 50. These argon 38, 36 ratios show absolutely no deviation, no matter how much mantle component is in that, from an atmospheric value. Mid-ocean ridge basalts are identical to air, identical to the well gases, and certainly no hint in the mantle supplying mid-ocean ridges of a solar component. We can't use this to say that the heavy noble gases are delivered to the Earth through chondrites, because we have to consider the possibility that air may be recycled back into the mantle, and that's something I will talk to in a little bit. We can look at the shielded xenon isotopes. The data is now lost a little bit. These are the xenon isotopes which are not affected by radioactive decay processes. These are the isotopes which preserve the source signatures within the mantle system. 126 to 130 ratio, 124 to 130 ratio. Air and all of the data from the well gases are close to the air value. But what you can see is that solar nebula, carbonaceous chondrite values cannot be distinguished using the xenon isotope system. We certainly have got a component within the well gases which are clearly primitive, but we cannot distinguish between the actual source. Krypton, on the other hand, is unique in the noble gases in that it can distinguish between those different sources. Again, we have ubiquitous air contamination. All samples lie on this mass fractionation line, but what you will see now is that the carbonaceous chondrite value is quite different from the solar nebula signature, and that now we have prima facie evidence that indeed we have from the krypton isotopic evidence mixing between air and something that looks like a carbonaceous chondrite, but is distinct from solar nebula source. So the heavy noble gases, as well as the neon, seem to be completely consistent with delivery to Earth as a trapped component within meteorites. It is worth mentioning that if you want to generate the atmosphere from degassing of the Earth, if you degas into the atmosphere a composition which is chondritic, you then have to fractionate the atmosphere. Most fractionation processes involve light isotope depletion, which will take you further up on this mass fractionation line. If your atmosphere is created by degassing of average carbonaceous chondrite and fractionation, you go in the wrong direction. This is very strongly suggestive that the atmosphere we have today is not derived principally from mantle degassing and fractionation, but must be delivered to the Earth in a different way. So what I hope I've done is build a picture of two accretionary volatile sources preserved in the Earth over geological time, over planetary history. The mid-ocean ridge source, the mantle dominating the bulk of our deep Earth, certainly contains a component which is completely consistent to be delivered by trapped in accreting material. But we must recognize that within the deeper Earth, if that's the source of the ocean island basalts, we're seeing a hint, a trace of something else which may well be the remnants of those earliest stages of planetary accretion, that is the nebula gases. And some very fantastic work from Sujoy Mukhopadhyay, published in 2012, strongly suggesting that this deep mantle reservoir has been preserved and has not contributed to the upper mantle regions, but has been preserved and has been isolated in the deep Earth, again, over planetary history. So we're starting to get a new insight into not just the sources of the volatiles, but how those different reservoirs interact. And we're still learning how to bring those components together and how to reconcile reservoir interaction. Part of the reservoir interaction is having created our planet, having brought the volatiles to the planet, having closed the planet to volatile loss, is there any subduction of volatiles into the mantle? Is there a mechanism which overprints those primordial components in the deep mantle? Certainly for a very long time in the noble gas community, there was a tendency that you could not subduct noble gases into the Earth. The subduction process was so inefficient that you completely stripped out volatiles, certainly noble gases, during the subduction process. And suitably named the subduction barrier. But I've already shown you that there are hints, not hints, there are significant components in the deep Earth which have an atmospheric, a modern atmospheric isotopic composition. So how do we get those into the deep Earth if the subduction barrier is in fact a real barrier to imprinting surface volatiles into the deep Earth? Well, it's possible that we can preserve components of the process which generates the atmosphere in its modern form, but it's very complicated. Certainly to put the isotopic composition of the modern atmosphere into the deep mantle, it's much simpler to argue that the subduction barrier does not exist, and I want to just show you some data which allows us to assess that in a little bit more detail. I've already shown you this radiogenic xenon diagram. I just want to point out that the highest samples that we've measured still contain about 50% air compared to the mantle end member, which is at the intersection of the crustal fluid array with the morb array. Even the best sample that we've actually measured is still 50% shallow air contaminated. We can correct for that 50% shallow air contamination. I've now moved to the shielded isotopes, but what you can see with this 50% shallow contamination is that we are still a very, very long way from coming close to any of the accretionary end members that we could use to source these gases. We have about an 80%. I'm losing my point. We have an 80% contribution of atmosphere to a 20% contribution to the from the volatile origin. Okay, so I've already said that the accretionary component, the air-like signature, if it is an accretionary component, must be fundamentally linked to the atmosphere fractionation formation mechanism. Or we're simply recycling noble gases from the modern atmosphere into the deep Earth, in which case we need a mechanism and we need to understand the consequence. Just looking at this a little bit, we've got a 130 xenon to 36 argon, 84 to 36 argon. So again, we're looking at the non-radiogenic, the primitive gases which have preserved source composition. We can see that the mantle component, and this is derived from mid-ocean ridge basalts, from the well gases, the mantle component is elementally now remarkably similar to seawater, with a small amount of excess krypton, small amount of excess xenon. If it is recycled components, we would expect there to be sedimentary components, pore fluid components, and we know that oceanic sediments have got a huge amount of excess krypton and excess xenon, which is absorbed onto the organic components and some of the mineral components within those altered oceanic crust. Tiny amount of ocean sediment, a seawater signature would certainly give us the mantle noble gas composition that we see today. So we have got one possibility that we've got an accretionary process-related component which by chance gives us an atmospheric isotopic composition and by chance provides an elemental composition just like seawater. I think that is just too much, and I think we can apply Occam's razor and simply reject that mechanism. The isotopic composition and the elemental composition in seawater today is unique in the solar system. To find that in the deep Earth, I would argue, suggests that we're looking at a recycled atmospheric component moderated by the seawater environment and implanted on the sediments which are taken down into the mantle system. And we can see that. This is a peridotite body which has been brought back up in Japan, the Akashi peridotite body. This is work of Hirochika Sumino. And we're now looking at, again, a noble gas fingerprint, noble gas pattern. And we're looking at the noble gas normalized to argon. And we can see that the krypton argon, the xenon argon, are again indistinguishable from those components that we measure in the mantle system. And by looking at the halogens within the system, we can look at the iodine-chlorine ratio versus the bromine-chlorine ratio. And this is a really nice experiment where Hirochika Sumino has irradiated the samples, converted the halogens to noble gases, and by heating the samples, decrepitated all of the serpentinite, which is and secondary alteration, pumps that away, crushes the samples, and just releases the serpentine, which is the fluid-rich component within the olivine system, to be sure that he's sampling the halogens from samples which have reached 90 kilometers in depth in that subduction process. So we're looking at inclusions which have got a bromine-chlorine, iodine-chlorine ratio indistinguishable from marine pore fluids. The noble gases are indistinguishable from marine pore fluids. We have a mechanism, we have observations which support a mechanism of taking that signature at least to 90 kilometers depth in the subduction process. If it reaches that far, there's no reason to think that some of that signature cannot travel deeper into the mantle and give us the signature that we observe in the well gases and at the mid-ocean ridges. We certainly don't believe that the subduction barrier is 100% efficient. The noble gas pattern of marine pore fluids is preserved. And this is very important. If we are preserving that noble gas composition of seawater, any fluid loss would massively fractionate that pattern. If we're preserving that pattern, that suggests that the fluids associated with that seawater signature are also trapped within that unit volume. And we've used that to do a simple calculation inferring that the water associated with those noble gases is also there. And to account for the noble gases in the mantle, we need about a 9% subduction efficiency of the water passing from the subduction zone into that deep mantle. We can compare those to recent models. This is a really fantastic piece of work by Peter van Kekken and co-workers, JGR in 2001, looking at the thermal control in the different subduction zones today and how the different thermal control, how the different thermal regime controls mineral breakdown and water loss from the different environments, the different subduction zones around the planet today, allowing him to assess the percentage of water that may make it into the deep mantle. And he estimates today we're looking at about 32% of the water available being carried into the deep earth. We're looking using the noble gases at about 9%. This is a minimum value, but I think we might suggest that we're looking at changes in the subduction efficiency, temperature decrease with time. As temperature decreases, subduction becomes more efficient. How much time have I got, Bob? 10 minutes, great. I just want to finish by talking a little bit about halogens. I've introduced some of the information that we can get from halogens. I want to particularly mention one of my colleagues, Ray Burgess from Manchester, who's really been fundamental in developing these techniques and driving the use of the technique of irradiating samples, converting the halogens to noble gases, measuring the noble gases to derive the halogen content. It's an adjunct to the argon dating technique. But what it does allow us to do is probe samples at an unprecedented level for the bromine content and the iodine content. And because the halogens are highly incompatible, fluid mobile, they've got a lot of characteristics which are similar to the noble gases. We're looking at the halogen content through the oceanic crust. We can see a poster being presented this afternoon by Deborah Chavrit. We can see the mineral control, the altered oceanic crust, the shallow seawater hydrothermal alteration versus the deep, high temperature, low fluid to water ratios control the halogen content of the oceanic crust, control the noble gas content of the oceanic crust, and certainly provides an opportunity to test, when we're looking at surface-derived fluids, the environment or the portion of crust that has released those samples. We're developing new databases to understand how noble gases partition when you've got a melt, so looking at melt fluid, rather melt solid control of the halogens. We have no database at all for the bromine and for the iodine. I've shown Bastien Joachim. This is showing his recent fluorine results, but he's also got the first preliminary data for bromine partitioning. So we can really start to look at the halogens and use the halogens in a quantitative sense once we start developing these partition coefficients. We're getting a better understanding of halogens in the accretionary components that can deliver volatiles to the Earth. Trish Clay is giving a talk on Thursday. She's got a fantastic data set of a variety of carbonaceous chondrites, enstatite chondrites, and is showing how the functional modal mineralogy really controls, and thermal processing really controls the halogen composition, and has reduced significantly the range of halogen concentrations expected, showing certainly that carbonaceous and enstatite chondrites today certainly are much closer to the territorial morb and bulk silicate earth fields than we've previously thought. Back to the mantle. We can look at the heavy halogens and how we can understand their concentrations and how we can understand the processes controlling their concentrations in so much more detail today. This is a study that's not yet published by Lorraine Ruzzi, looking at the central Indian Ridge. And we're looking here at potassium chlorine, potassium bromine, but what you can see is enriched mid-ocean ridge basalts, normal mid-ocean ridge basalts, water content, all correlating very nicely, allowing us to pin down the concentration of the halogens in that source region. Now, I'm coming full circle now. I want to talk a little bit about iodine. Our estimate of iodine in the Earth has been very, very poor. No work until 1992. Deroule produced the first estimate of iodine within the Mantle system. Ray Burgess, through a study of diamonds, suggested the iodine content was a lot lower at 0.4 ppb, and Lorraine, from a central Indian Ridge work, suggests that the iodine content of the mantle is lower still. The iodine content comes right back to some of those slides that I was showing you at the beginning, where we can consider the amount of iodine and the closure age within the mantle system itself. We can do a really simple mass balance. We can look at the mantle concentration. Looking here, I'm using the Deroule value of 0.8 ppb. It is simply not enough iodine in the Earth to produce the 129 xenon also associated with that portion of the mantle. We simply do not have enough iodine to produce the 129 xenon existing in the mantle system. We need either a separate 129 xenon source, which is not feasible, or we need to recycle atmosphere containing excess 129 xenon into the deep mantle. We can model the amount of recycled xenon, and the requirement for the amount of iodine we now need in the mantle at the de Roule concentrations suggests that we need about 70 to 80% recycled xenon at a xenon closure age of 100 million years to balance our understanding of the way the mantle in its earliest period lost its gases. If the mantle really is 0.4 ppb or even lower at 0.1 ppb, we don't even have enough iodine in the mantle to account for the 129 xenon, even if we have 100% recycling. We can't do it. We have to then assess the fundamental calculation we've made to derive the closure age, and it certainly would point then to a lower closure age on the order of about 80 million years rather than 100 million years to reconcile these very low iodine concentrations that we're now deriving in the planetary system, in the mantle system. So I will conclude there. I hope I've given you a sense that over the last decade, we've really developed a new view of planetary volatile origin. There may well indeed be in the deep Earth this remnant of solar nebula gas capture. The bulk mantle is dominated by volatiles delivered by solar wind irradiated carbonaceous material. The Earth has undergone massive planetary interior and exterior atmosphere loss. And perhaps the atmosphere has been added through late addition of a water-rich component. The subduction barrier certainly does not exist for the noble gases. Noble gases are recycled into the mantle system. They provide a way of quantifying and testing recycling. We can start now linking those noble gases to other components. I've shown you how we've started to work with the halogens. And certainly in the case of iodine, it's allowing us to really test some of those fundamental ideas of how the mantle behaved in the earliest period of Earth history. Thank you for your attention.
Thank you. So if the subduction barrier is not there, can you revive a very old hypothesis by Allegri, which says the deep helium signature actually is subducted solar helium? And also the same for neon, too.
Well, I don't think it's me reviving it. There's a nice paper by Tolsky and Hoffman, 2005, 2006, which suggested that in the early stages of accretion, that a dry subduction may have taken solar wind irradiated material down into the deep Earth. But so I think subduction and transport of volatiles into the Earth is certainly happening. And dry subduction may well be more efficient than wet subduction we're seeing today.
Yeah, but Allegri's model was that it's a continuous, steady-state process. So we are subducting enough helium-3 into the mantle, and that's coming up roughly the same amount.
No, certainly not. There's nothing to support in ocean sediments helium-3 flux, which could match anything coming back out. So there is not a helium-3 subduction that has been continuous or is current.
Chris, could you provide us with a little bit more background on exactly what nature of the samples there are that are providing this extremely low iodine concentration of 0.1? Because the implications of that discovery are so huge. What's the breadth and nature of those samples?
Well, these are mid-ocean ridge samples from the central Indian ridge. So this is the basalt samples which have been analyzed for their halogen content. And this is very interesting because I think we need to understand why in the past people have thought the iodine concentration is higher than the values that we're looking at. And there's it's already passed, but Michael Broadley presented a very nice poster just recently looking at how the basalt glass rind on, so this is the glass rind on a basalt pillow, how the very outer edges of that are extremely contaminated with high iodine concentrations. And it may well be that lack of sample control has provided higher than real iodine concentrations. And through careful measurements and also through seeing those systematic behavior from normal morb to enriched morb with water content, those all provide confidence that you're not seeing contamination process, but you're seeing source signatures.
I'm sure you thought about the DH ratio in the Mantle, the long-term evolution. What's your take on this? Because if you subduct water with the delta D of 0, you either fractionate it and you lose your rare gases, or you don't fractionate and then you get down towards, you get up to 0, delta D of 0 with that kind of process.
Yeah, we in the paper we published in 2006, we did the deuterium mass balance and showed that there's so much uncertainty in the original deuterium content of the deep planet that putting a 9% delta D of 0 into the mantle was certainly within allowable limits. But it's a good question.
Yeah, this was one.
No escape.
Hello. Maybe last question. About iodine, we performed some experiments between metal and silicate partitioning, and we found that the core can take 1 order of magnitude concentration higher than the mantle. Can this change anything in your models? And second part of my question, does the Earth's core can have any impact on the volatile in the mantle?
Could you repeat the first part of your question?
We found that iodine is siderophile during the Earth core formation. So the core is having 1 order of magnitude higher concentration than the mantle. So the question is, does the core can have any impact on the volatile in the mantle?
No, I think that's very interesting. I'd like to see that, because if the core formed while iodine 129 was still active, and you are correct that it can sequester iodine into the core, then it is a potential source of 129 xenon, which we are short of.
Okay, could you all join me, please, in thanking Christopher for the talk?
Thanks.
And we'll look forward to seeing you again tomorrow.